The second part of 2.2 continues working with functions. In the first example, we're going to evaluate a function using a table. Complete the table for f of x equals x squared minus 4. Notice in the top row, x equals -3, -2, 0, and 2. To get what f of x, or our output, would equal, we'll just substitute -3, -2, 0, and 2 into our equation. When x equals -3, I'll take -3, the entire quantity, and square it. I'm squaring whatever x is, and then subtracting 4. -3 squared would be +9, and 9 minus 4 would be 5. The next one, -2, pretty much the same idea. Just take -2 and square it, and then subtract 4. -2 quantity squared is 4, and 4 minus itself is 0. Now if we plug in 0 for x squared, that would give us our y-intercept, and 0 minus 4 would be -4. And we know that quadratics are symmetrical, so now watch what happens when we plug in +2. +2 would give us 2 squared minus 4, and 4 minus 4 would go back up to 0. Just evaluating functions in table form versus what we did in day 1. Piecewise defined functions are functions defined by separate equations over specified domains. So what that means is you can have more than one formula for given values of x. It says given f of x equals x squared plus 1 when x is less than 0, and then x minus 1 when x is greater than 0. That means you'll plug it into the top row, so plug in here. If the value for x that you're using is less than 0. Otherwise, plug in here, in that second row, if your value for x is greater than or equal to 0. Ultimately, you just want to figure out which row makes sense for your value of your input. So let's try just a couple of examples. In the first example, x equals -3. Now, is -3 less than 0, or is it greater than or equal to 0? Hopefully we recognize it's less than 0. That means we'll plug it into the top row only. It only works when x values are less than 0, and that's what applies here. So if that's x squared plus 1, and x is -3, we'll just take -3 and square it, and then add 1. -3 squared is 9, 9 plus 1 is 10, and that's your output. Let's try another one. X equals 0. So now be careful, because if it equals 0, it can't be plugged into the top row. Equal to 0 isn't less than 0. In that second row, x is greater than or equal to 0, it will apply there. So that means we'll go into the bottom row. And we just plug in x and simplify in that bottom row. If x is 0, then 0 minus 1 is -1. That's it. That's really all you do. Now for that last one, x equals 6. 6 isn't less than 0, so we're not going to plug it into the top row. 6 is greater than or equal to 0. That's true. So we'll plug it into the bottom row. Now you don't have to write top row, bottom row. That's fine. Just make sure you know which row to plug it in to get your correct result. X minus 1 would be 6 minus 1, which is 5. And that's working with finding piecewise defined values in functions. Finding values for which f of x equals 0. When this is what's being asked, what you want to do is just set the equation equal to 0, like we did in quadratics when we solved for x-intercepts, and then solve for x. Now if it's, well, that's an exclamation point. It's that important. There we go. Let's fix that. There we go. Now, if it's a linear equation, you're just going to have one solution for x. If it's quadratic, you may have more than one. Find all real values of x for which f of x equals 0. What you do first is just set the equation equal to 0, like we did back in topic 1b. Oopsie, doesn't look like it's easy to read right there. Let me try that again with my pen. So let f of x equal 0. 0 equals negative 2x plus 10. Now, solve for x. We want to get x by itself. Let's move 10 over by subtracting. 0 minus 10 is negative 10. And what would we do now to get x by itself? Divide both sides by negative 2. The negatives and the x's cancel, the negatives and the 2's cancel. On the left, negative 10 divided by negative 2 is positive 5. That is the real value for x that makes the output equal 0. Now, over on the right, same idea. Find all real values for x for which that function equals 0. Just means we're looking for x-intercepts. Start by setting that left side equal to 0. If we remember quadratics from the last chapter, we had a couple of options for solving. We could factor, and we could do quadratic formula. To factor this actually will be pretty easy. There isn't an a value out in front to multiply by, so what we need to do is split c. Think of numbers that multiply to get 6, but add to get negative 5. We could do negative 2 and negative 3. That would mean we'd have 0 equals our 2 parentheses, x squared splits into x times x, and then minus 2 minus 3. Now apply the zero product property and set each parenthesis equal to 0 separately. Hopefully this sounds like review. We just covered it in our last topic. So one value for x that makes the f of x function equal 0 is 2, and the other value is 3. We have two solutions here. And that's finding values for which f of x equals 0. The last part of 2.2 says given f of x and g of x, so now we have two different functions. For what values of x will the functions equal each other? So you're literally just going to start off by setting them equal to each other. Whoopsie, there's my h. And then solve for x. In the first problem, f of x equals x squared plus 1. In the second, g of x equals 3x minus x squared. Start off by literally just setting them equal to each other. X squared plus 1 equals 3x minus x squared. Now, because we have a quadratic equation, we need to solve for x by getting everything equal on one side and setting it equal to 0. So now we're going to set equal to 0 again, like we did up above. To do that, I'm going to add x squared to the left and subtract 3x. If I move everything over, we end up with 2x squared minus 3x plus 1 equals 0. And you might have to write kind of small in here to get this to fit, so use all your space if possible. Notice now we have an a value that's 2. That's going to require us to use that earmuff method where we circle the a and the c and we multiply. 2 times 1 is 2. Now think of factors at 2 that would add to get negative 3 in the middle. Well, if we use negative 1 and negative 2, we would get that to work. So now we split the b and we write out 4 terms instead of 3. The first term stays as is, remember, 2x squared. And then in the middle, I'll do minus 1x minus 2x. Those two get what 3x was initially. And then I'll put plus 1 equals 0. And now group the first 2 terms and the last 2 terms. Then we test for a common factor. This is all review from the last chapter. In that first parenthesis, all they have in common is an x. And then we'd have 2x minus 1 left over. Now in that second parenthesis, we have to factor out the negative. And I don't think anything else comes out of 2x and 1, so I'm going to put a 1 as the placeholder. If you factor out negative 1 from negative 2x, you'd get positive 2x. And if you factor negative 1 out of positive 1, you'd get negative 1 left over. Notice the parentheses match, so at least we're in good shape there. 2x minus 1 is one factor. And then the parts on the outside, x minus 1, make up the other factor. Once it's set equal to 0, apply the zero product property. In that first parenthesis, solving for x would give you a value of 1/2. In the second parenthesis, solving for x would give you a value of 1. So there are two solutions that you could plug in up above and have f of x equal to g of x. Let's try one more. Same idea, another one that has quadratics. Now f of x equals x squared minus 1, and g of x equals negative x squared plus 1x plus 2. If we start off setting them equal to each other, we would get x squared minus 1 equals negative x squared plus x plus 2. Because it's quadratic, again, like the last example, set everything equal to 0. So I'm going to add x squared to the other side. And I'm going to subtract the x, and I'm going to subtract the 2. And then try to combine all my like terms. Now I have 2x squared, and only one x term, and it's negative. And then negative 1 minus 2 is negative 3. Once you have your quadratic equation equal to 0, we have to solve by factoring our quadratic formula. And the quadratic formula always works, but I think this one will factor. Let's try. Positive 2 times negative 3. If we multiply them, we get negative 6. Can you think of two numbers that multiply to get negative 6 and then add to get negative 1? Be careful here. Only one pair works, and that's going to be negative 3 and positive 2. 6 and 1 won't work, so make sure you're careful on that. Okay, so once we know our factors, here's your 2x squared, and then we'll have minus 3x plus 2x, and then that last term, minus 3, equals 0. Group the first two and group the last two. In that first parenthesis, again, only x can come out of both of those terms, and we would get 2x minus 3. Now what's happening in the next one is actually nothing comes out unique to factor out of 2x minus 3. Therefore, the placeholder would be 1. And if you factor 1 out, it stays 2x minus 3, which is good because now we have matching factors. 2x minus 3 for the first parenthesis, add the parts on the outside, x plus 1 is the factor in the other parenthesis. Once we're here, it's that zero product property again. 2x minus 3 equals 0. X would equal positive 3 over 2. And then x plus 1 equals 0. And x will equal negative 1. Those are the values for x that make that equation, or make the two equations equal to each other. Your assignment for 2.2, day 2, is on page 183. For 31 through 34, you're just evaluating functions and include a table for each of your solutions, or for each of your problems. Then jump up to 36, 39, 40, 44, 51, and 52. Now you'll have time in class on Thursday to work on this.